Did you get the licensing for this, Alberto?
What we've been doing for the past 3 years. I'm Alberto, the founder of Perceptive. We have a lot to show today, and we're really looking forward to sharing with you our vision for the future of autonomy. I want to thank everyone for making it here, for actually being patient with the parking and finding a spot outside. I know it would have been awesome if we could have just been dropped by an autonomous vehicle, just not have to worry about leaving your car outside, and I'm sure Stanford would have loved not to actually occupy a lot with like 1 ton of metal idle. We could have got more students, more money. That's what we're doing. But we're here today because we are afraid that if we continue working on the same path we've been doing for the past almost 2 decades, we might not get there, not in any reasonable amount of time at least. It's okay. It's fitting we're having this event here at Stanford because it's been almost exactly 16 years since the Stanford racing team won a Dark Grand Challenge in 2005. It was October 8, 2005, with a team led by Sebastian Thrun. Some of the people who were in the team are actually here in the audience, so it's exciting. I don't know if you still celebrate on the day. And we made tremendous progress from those days, right? We have commercial robotaxis now being deployed across the country in several cities, going actually more and more. Lots of work has gone there, but let's be honest, true, really driverless autonomy, the stuff we've been dreaming about, the stuff that will change our mobility, that will enable disabled people to go anywhere, that will change the landscapes of our cities. All those things, we've been talking about is not here yet. And we're wondering why, as the famous Hans Moravec actually here at Stanford put it very well in words about 50 years ago. The truth is, when it comes to AI and robotics, and you all know about this, it turns out the hard problems are easy. It's the easy problems that are hard. When it comes to computation, winning a chess, winning a Go, relatively easy. When it comes to perception and mobility, we're actually still quite behind compared to even just a 1-year-old child. Why is that? Why is that? I think that's what is holding us back. Somehow, many of us have hoped or kind of been operating under the assumption that if we could just brute force our way through the problem, we could actually get to a solution, And, we've been told that, just add more compute, more sensors, more training data, and we're gonna have it. And it's 2021, and it's constantly a few years around down the road, right? And it's still there. And this idea of the brute force is so deeply ingrained in the industry. We're operating along these lines sometimes without questioning much about it. Many of us have been assuming that. So it's just we got the main framework in place. It's correct. It's just about optimizing. So this is just an optimization problem at this stage. It's not. It's time we actually stop for a moment and consider those assumptions that we've been giving for granted, not even discussing them for the past 16 years, right? And if you actually look at how the way we've been doing this for the past 2 decades, so you can across the industry, pretty much everyone at a high level, there is a common approach, right? It's a famous 4-tier approach where the vehicles first kind of sense the world, and then they try to perceive with the idea, okay, first you get sensing, then you extract meaning from sensing, and then you plan what to do, and then you actually drive around, right? So it's like very linear, bang, 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 4 tiers, it's very logical, right? It seems like intuitive, that's how we solve the problem. The thing is like, this was very fair and definitely a good way to solve the problem 16 years ago, but we know much more today, we learned a lot, and it turns out this separation so neat between the blocks is an oversimplification. Things are more complicated than that. We're missing out a lot of the deep interconnections and interplay between these blocks that you cannot just split at this level. And so if you actually look deep down how the system works today, you realize that how it's made. Actually, first you cannot even properly call it a system because it's mostly there's no real system level thinking. It's not like a top-down approach. It's actually very much bottom-up. It's kind of emerged and evolved during the years in this trial and error without everyone really being a mastermind of this. It kind of just happened this way, and now we're operating along these lines, right? How is it made? You get at the base like a ton of like third-party sensors, right? Usually they're black boxes. They're not intelligent. The little bit of intelligence they have inside you don't see. So everyone is effectively sitting on third-party black boxes, and everyone is building safety-critical application as a big unknown layers under the floor, right? They don't talk to each other, the sensors, right? LiDAR, radars, cameras, they don't talk with perception, they make no assumptions about the world, and they waste 99% of the data they produce because all the raw data goes to waste, right? And it's a huge problem. Like, again, it's as if you're a professional photographer. We have some in the audience today, and you're trying to make beautiful pieces of art, and all you can work is like ultra compressed, maybe 1 kilobyte files, even if you have a super 40 megapixel camera. And to try to solve the problem, you keep buying more and more expensive camera, more complex, and you keep working in 1 kilobyte files, right? Nothing is going to change. So somehow the industry, the AV industry, is kind of stuck in this paradigm. They keep buying more expensive cameras, but they keep working with these ultra compressed files, right? So the approach is a problem. And then, the kind of assumption you get all these sensors, there are dozens of them, they're a nightmare, everyone knows, but you know very well. You put them into these like fusion boxes that are supposed to aggregate, align, and superimpose these sensors, and then you pipe this into AI, which is downstream. So it's very much one directional. It goes only one way. So this is like the cause of the brute force, or the incarnation of the brute force technology that we have today. So we thought that this is actually missing out the true quality of perceptions that and sensing that we have in humans, right? So if you actually look at what we don't have, what we're missing out, there's a couple of key qualities that sensing and perception system of humans has that we haven't been able to put into the systems, right? There are some key aspects that we're missing out, and somehow we're thinking that we could leave aside and somehow keep going. But one aspect, first and foremost, is in humans, sensing and perception are actually one and the same. There is no such a thing as a sensing stage and a perception stage, or just so you create data and then you pass it to an interpretation layer in our brains. No, the two things are so deeply interconnected that you cannot even really distinguish them, right? And then another very, very key aspect that also we haven't captured in those systems that we've been using for the past 16 years is that in humans, again, perception is a creative process. So what we actually perceive is not just a projection, the distillate of our sensors is actually a sort of like a virtual reality that goes on in our mind that we produce ahead of time. And what sensors do is actually make sure that we keep it in check. So sensors are sort of like a reality check on this virtual reality we have in our mind. And that's actually the brilliant way that nature has been able to give us to solve the problem of bandwidth, but also time. Like this is the way we can actually really make sense of the world with finite computational capacity, very little time, and always be ahead of the world. Because you cannot be behind the world. You cannot wait to react to the world. You'll be always like a little bit a step ahead. Otherwise, you don't make it very far in the evolutionary ladder, right? So these are key aspects that we've been missing out, and we need to try to recapture. So these are kind of almost familiar to everyone, right? Like think of like aspects like color. You would think color is the most objective quality you can think of. Like if you're a physicist, you take a wavelength meter, you We can measure exactly what a color is. There's no such a thing for us. Color is extremely subjective, context dependent, right? Psychology dependent, very opinionable, right? As you know, the famous black, blue dress or white and gold, right? You can find people thinking in all possible ways. It's actually often in the optical illusions that like cognitive psychologists and neuroscientists love, that you can actually see it's kind of our system at work. You can understand this mechanism of perception and sensing. Like, the internet is full of these things you can probably find and get lost in. There's like something really fun. You might have seen the famous hollow mask, which is a typical, very, very strong example of how our biases are so deeply ingrained in us. Like, for instance, in this case, the bias is that of the faces tend to be convex. We don't see concave faces in reality, right? And when you actually are presented by a concave face like a mask turned the other way around, our brain just rejects it. It does not accept it, right? So that shows that actually, to the point that actually the brain starts actually changing the direction of rotation of the mask. So, I mean, granted, this is actually a failure of our cognitive system, right? But it's enlightening. It shows actually how we operate. And we can do better than that, because biases are powerful, but they're also, in our case, deeply kind of hardwired in our DNA. Whereas in our computational system, we can do better than that. We're not constrained by hardwired biases. So these things really show that sensing and perception are something much more profound in humans, right? And the brute force approach really just now reproduces it. There's nothing bad with brute force. Let's put it like, it's okay, it's fine. And we should use as much as we can. But what if it's not enough? What if we're not getting there? We use it all and we're still not there yet. What do you do, right? I think something fundamental is amiss. That's what we're living out. And so for actually, when we started Perceptive, we really wanted to change this completely. We want to start a new era where we actually look at electronics in a different way, where we actually sensing and perception are actually united and brought back together into a novel system that actually tries to capture these fundamental qualities, so we can actually simplify our system, simplify our compute, simplify our sensors, and just using a truly, truly perceptive and intelligent system. So with this big goal in mind, right, we started in 2018, like a little bit more than 3 years ago, about this summer, I remember very well. So, and we were engineers, we're dreamers, very ambitious, and we went to the board, and we started like, we want to change this. This is not working. We have to rethink it. Let's think about how would you like the system to be. So we cannot come up with a wish list at the time. And it's funny because it's a wish list of the past, and it came out to reality now. But we thought, okay, first, this thing needs to be a system. Okay, let's stop having this like tons of like third parties and dozens of sensors that you need to speak different languages. They actually have low quality data output. You need to upgrade the firmware. And we've all been there at midnight doing this thing, and you depend on these people. You don't know how they work, and it's like such a thing. Huge, massive integration effort for all the AV companies in the valley. You know very well. Rabbit hole. The last year, by the time you finish, if you finish, you have a new generation of sensors, right? It's always like that. And it's a huge distraction for everyone, right? So I don't think we should be focusing on that, on massive integration efforts. The system, we also thought, needs to be intrinsically digital. Really, really purely digital, because the solution is in the software space, is in the data, it's in the algorithms, and you need to scale like a digital system. No more analog stuff, right? It has to be from deep down, from the core, it has to be fully, truly digital. It needs to expose all the raw data, because they said the information is there. We're throwing it away now. We're shooting ourselves in the foot. We're spending tons of money and we throw it mostly away. We're not capturing that. It's also when you don't share it, it's something that you hide into your customers, right? Other really important, finally give us machine learning in sense, right? We don't have it today. It's ridiculous, right? Absolutely. We know very well that's the way to actually simplify the hardware, making it more powerful, saving money, right? Bringing really intelligence to the sensor. We don't have it today. It's ridiculous. It's the least sensors is the least intelligent part of an autonomous vehicle today. Unacceptable, right? And then finally, let's focus on software application, actually solving a problem in the software space, and actually defining sensing modalities, defining these novel ways to actually interface sensing and perception in the software space, so that we can actually improve at the speed of the algorithms. We can scale with the compute, we can scale with more loads. And at that point, kind of the sky is the limit, right? It's just people's ingenuity and the limit. And so in this way, make it open, completely certified, because there's no way, no absolute way anyone is going to put lives and people in boxes if you don't completely own the code, the logic of these things that you're sitting on top. So absolutely, there's no way. No agriculture, no robotics, no cars, right? And that's not how it is today, right? Certifiability, as we move from this demo mode we've been for the past 16 years to true product, right? There's no way around that. And it's not possible with today's systems, right? It's a big block. And so we went and we decided to build this. And we actually picked a very powerful architecture. We decided to design kind of inspired by the computer architecture. So it's a 3-tier level system. So at the base, we have a hardware layer that is universal and general and agnostic to actually the sensing technology you adopt. The idea is to just function as a conduit for sensing information coming back from the environment, not to make any decisions about the environment yet. Just the idea is to channel and funnel that information up higher at a higher software level. On top of that, you actually have an abstraction layer, like macOS or Microsoft Windows, that hides and kind of conceals all the hardware complexity underneath. If you're on a computer, you don't need to know anything that's under your case. All your world lives above the OS, right? And that's where perception and sensing need to happen, as applications and the software modules operating up high in the software stack, right? Not deep down, up high, so everyone can actually continue to develop. So that was like the key kind of the blueprint we assigned for ourselves. And it was a big, big taking because you saw all those elements in our wish list that are huge, right? Each of those could be a company, right? So you think how you actually do it. Small company, starting from scratch, a huge deal, and you kind of have to have it all. Well, the thing is, if you actually get the right architecture, the right core technology, it all falls into place. They all come together. You don't have to actually get them all. You just have to pick the right core technology. So we did just that. Over the past 3 years, we went from drawing board to the lab. We built this secretly, or for some of you, maybe you got a sneak peek. And we're so really thrilled today to show you what we've done. And now it's actually coming out to the world. This is available. And to tell you all about our specific application to driverless vehicles, level 5 vehicles. I want to invite our VP of Engineering, Reza, here to tell you all.
All right, thank you, Alberto. I don't have Alberto's fancy clip-on mic, so I have to be here. I can't show you my dance moves, but we are very excited to be here with such a great audience and show you what our team has been working on for the past 3 years. We have been busy at work designing and building the only full-stack solution for level 5 autonomy. And ladies and gentlemen, here it is, right here. Woo. So let's start by looking at the design. One of the key design decisions we made early on for our product was to separate probing from sensing. Starting from the exterior of the vehicle, we have a number of multimodal probes that can be placed at any position. These probes are small, they're nearly passive, they're inexpensive, and they're extremely robust. Right here, this is one of our laser probes. As you see, it only takes up a few cubic inches and can be placed anywhere around the vehicle. To draw an analogy with us humans, the probes are basically like the eyes and ears of the autonomous vehicle. Just like our eyes and ears, there's no logic or compute happening in the probes. Basically, all they do is they collect rich, raw signals from the environment, and they pass the signals to the central platform you see here over optical fiber links. And we did not use fragile optical fibers here. These are rugged, heavy-duty, military-grade fibers. You can twist them, you can bend them, you can bang on them. They're not going to give up. Then we have the central platform here, which is essentially like the brain of the system. It is housed inside the vehicle cabin, and it is where all the critical hardware components are centralized, and it's a unified place where all of our software runs. So all your important hardware modules like the power distribution module, optical modules, RF modules, and all the compute is integrated into this one box. So everything is safely housed away from the environmental elements outside the cabin, and all the hardware is shared between the multimodal probes. So let's take a closer look at the multimodal probes that we have around the vehicle. The key to making this all work was a unique proprietary technology that we developed called digital sensing. These probes are multimodal and can use different means of probing the environment, such as laser beams, millimeter waves, light, or ultrasound. But the unique thing that our central platform does is that it digitally encodes all the information that is relevant to perception and sensing onto these carrier waves. By doing so, we have essentially reframed sensing as a digital communication problem. So we essentially send out digital data packets into the environment, and we collect what's reflected from the targets through the same probes. So the sensing problem now becomes a problem of sending and receiving digital data packets, which has been figured out by the telecommunications industry for decades. That enabled us to use off-the-shelf digital communication modules in our central platform, the same kind of modules you see used in data centers today. And the first thing that happens inside the central platform is that we convert back the raw received signals to the digital domain, and then we can entirely build the multimodal sensors in software. By doing so, we can greatly reduce the size, cost, and complexity of the hardware, and greatly enhance the system performance and flexibility by making all of the sensing entirely software defined. If you look back in time, you see that one of the key enabling technologies for the internet revolution and later the AI revolution was actually digital communications. We at Perceptive believe that digital software-defined sensing is going to be a key enabling technology for the autonomy revolution. I should also point out that although here we are showing a use case of our product for an autonomous vehicle, it is architected in a way that it can be immediately used in other applications, such as avionics, agriculture, manufacturing, and robotics. You can easily imagine the same product being deployed on a factory floor or an airfield. Essentially, all you need to do is to pick optical fiber lengths of the right length that match your application, and everything else can just work. And these fibers can be arbitrarily long. So let's see how we have architected all of this. As Alberto pointed out in the blueprint of our system, from the beginning, we had set ourselves a grand challenge of designing and building a single unified system for perception and sensing. We have architected this as a distributed compute platform. We've started by what we call the digital sense front end. The digital sense front end is a universal front end that is essentially agnostic to the nature of the incoming signals from the probes. So the probes can be LiDAR probes, radar probes, cameras, IMU probes, GPSs, essentially anything can plug in and interface with the digital sense front end. We have designed and built a number of different probes for our system. As you see, this is the radar probe here, camera probe, and LiDAR probe. But third-party probes can also easily integrate into our system and interface with the digital sense front end. Now, as you can imagine, in order to be able to handle and interface with a large number of multimodal probes, the front end would need to be able to handle massive bandwidths of data. The front end we have in this central platform here has been designed to handle an I/O bandwidth of 3 terabits per second in real time. Let's put the number in perspective. 3 terabits per second of data in real time is equivalent to 180 fourth-gen PCIe lanes running in parallel. It's equivalent to 310 gigabit per second Ethernet links running in parallel, just to carry the data. If you wanted to consume this amount of data on an off-the-shelf PC, you would need 12 state-of-the-art GPU cards running in parallel at max capacity just to move that much data. It's a respectable number. Then the first thing that the digital front end does is that it leverages the fact that all the information is digitally coded into the raw signals, and it losslessly compresses the signals by a factor of 100x and reduces the bandwidth to something that can be easily consumed by the CPU and the GPUs on the higher layers of the compute platform. I want to emphasize that the kind of compression we do here is proprietary and it's lossless, meaning all the nuances and rich features in the raw data is preserved. Then on top of the digital sense front end, we have built the Perceptive OS operating system. The OS is essentially like an abstraction layer between the hardware front end and all the sensing and perception applications that run on top of our platform. The OS takes care of the high bandwidth network traffic. It runs FPGA driver software, and it handles all the command and control engines for the hardware front end. And in addition, there are a number of digital signal processing algorithms running on the OS and some deep neural networks for feature extraction from the raw signals. So by doing so, the OS essentially virtualizes the hardware front end for the application developers on our platform. The developers would have access to rich raw data through the OS, and they would also have full flexibility to control and reconfigure the hardware front end in real time, however the application requires. Finally, we have the Perceptive sensing software running on top of our OS. The Perceptive sensing software is a completely open platform where developers can build all kinds of sensing and perception applications using simple and efficient programming tools like Python, C++, and CUDA, running on CPUs and GPUs. The developers developing on our platform will have access to generalized raw data through the OS. This is raw data that is multimodal, and it's already time-stamped, synchronized, and packetized by the OS, and it's ready to be consumed by the applications. This enables a unique new methodology for multimodal sensing that we call concurrent sensing. So the OS effectively builds sandboxes for the developers where different applications can subscribe to different data pipelines, and they can also publish their outputs to the OS. The application developers also have access to a number of extremely useful APIs through the OS that expose all sorts of command and control hooks to the hardware front end. These APIs include LiDAR attention guidance API, MIMO radar configuration API, camera, IMU, and GPS APIs, and much more. So if you look at this architecture here, you realize that we have taken extreme care not to have any black boxes anywhere in there. The developers and the end users will have full visibility to the entire code and everything that runs down the hood. And this will make the certification process extremely easy when the time comes. Finally, we have not forgotten that a number of our users in near term are going to look for a turnkey solution for their sensing and perception needs. So the Perceptive OS comes with a number of native tools and applications that we have developed in-house, as well as a number of applications that our great partners are developing on our platform. These applications would immediately enable concurrent sensing, data visualization, and lots more. We're extremely excited to show you now some of these unique applications running on our platform. Back to you, Albert.
Right, here it is. It is something like you've never seen anything like this before. I mean, Reza mentioned it. The separation of sensing and perception is a game changer. Again, there's nothing happening here. Sensing is happening here. True sensing. You can design it from scratch. It's a canvas for you to design sensing methodologies, right? That's where the industry needs to move. That's where the focus should be, right? So we're excited to show you a lot of the application that we started actually developing on this, us and our partners. And so we talked about perceptive sensing, and it's so powerful because finally you can interface sensing and perception on a completely new computer. You do that on GPUs and CPUs. You're really defining your modalities on GPUs. You can do things you've never done before. Like you completely changed the logic and the nature of this entire space. And so I wanted to tell a little bit about how like this concept works, and which is really important because that's actually how we win. You know, one of the problems with sensors today, they're a little bit sort of like crude and a little bit, I would say, yeah, but they see the world in black and white. You know, either something is there or it's not out there. And you know, the world is more complex than that. Things are more complicated. And it's exactly when things are in those shades of gray that actually lies the opportunity to do more, right? And then so think actually the signals that usually come to a sensors, like they're not fully determined. They're sort of a little bit fuzzy. They're noisy, uncertain, and you still don't know what they mean. And usually today, sensors, they're very strict. They either tell you something or not, and you lose all this stuff in between. No, we actually savor. We look at the signal. It's not clear what to do about that. So we actually start looking at it, our system, our perceptive sensing system, sort of like a detective on a murder scene, right? And then what do you do when you're in a murder scene? You start collecting more clues, right? You look around, you look at the signal, you look at the additional insights and signatures on the signal. You enlarge your pictures. You go there and you write all these little details because there's a ton, huge wealth of information in the signals coming from the world. Much more than just beyond X, Y, Z and position in space. There are features carried from the light, whether it's optical, millimeter wave, or passive optical, due to the interaction of the light with the object. It tells you a lot about the world. You cannot throw it away. Okay, so your detective goes and it takes all these additional things and things start to make a little bit more sense, right? And then you start actually looking at all the modalities, like a detective will talk, to all the possible witnesses, and you start collecting different pieces and see how whether things match or they don't, right? You look for cross correlations between what people are saying at the really low level, at the signal level. We're not talking at high, really at the early stage. And then what do? You look at the context. Try to see whether the picture that is emerging is making sense to what you would expect. You look at the temporal context, you look at the spatial context, because now when you look at a signal, you don't look at it in isolation. You look at it compared to all the signals coming from adjacent regions in space, a moment before in time, a moment from now in time as well. So you cannot collect all that. You wait to make that choice. And then you filter that to your creative process, your expectations. We don't look at the world with a blank slate. We have biases, we have expectations, and they tell you something, because some things make sense, some things don't make sense, right? If it walks like a duck, and it looks like a duck, and it sounds like a duck, then sometimes it's a duck. But if you don't live in a room, and you've never seen a duck in your living room, and it's dark at night, maybe it's not a duck, right? Something like that. And then, then you actually have so much information now. Now you can make a much more confident, expert, wise decision, right? You just say something like, it's like we put it like a little Schrodinger's cat of quantum mechanics. It's like in this mixed state of half alive, half dead, right? So this is the data, right? And at some point you actually be able to say, oh, no, it's alive, no, it's dead. You actually can resolve the space. And you know what? This process you keep doing over and over and over, you get better and better at it. You learn. You feed back onto your expectations. You feed back on how you actually weigh all these little components. This is a neural net. So this is a truly intelligent system. It works like us, right? Much more contextual, much more sensible, right? So that's perceptive sensing. That's really what we actually do. Every signal, everything you're going to see runs through this approach, this framework we put in place. Something like this, you cannot even build it and even think about doing it with traditional systems as today, right? You need a completely different architecture to look at the world in this deeper way. So let me show you a little bit before we go into the live stuff. Some of this, we talked about insights. There's much more in the data than just X, Y, Z, than just position in space. If you look at optical data, look at laser data, or millimeter wave data, there's a huge signature. If you look at the details of the light that comes back, that is very, very rich, extremely rich, multi-dimensional, it's a hyperdimensional, right? It allows you to identify a specific object, to allow you to better cluster, to classify, and to track objects, right? So all this story, all these parameters become additional dimensionalities. So instead of just having X, Y, Z, you have 20 dimensions that you can learn, and train on, right? Additional channels, for instance, polarization. It's huge. It makes a big difference. And polarization tells you much more about the object. Look at this case, for instance. This is like a static scene looking with a laser signal, for instance. And you can see this is a typical intensity return you will see from a point cloud. You see? Like you've seen these things before. Now, let's put your polarizing glasses like a little bee, like bees and insects look at the world. Different vehicles, different objects, they look very distinct. You can classify, you can segment on these things, right? Look at the wheels, look at the different paint. Huge, huge, strong signature. It tells you about the geometry of an object because the ratio between the polarization tells you about the angle of incidence. You actually start seeing the 3D space shape on an object. All this information is there. We capture it, we broadcast it, we learn it, we train on it. I want to show you some of this static, and we'll show you more dynamic stuff, but I want to kind of highlight a little fundamental logic going on. This is actually something amazing that you get from a system like this. You can literally see through objects, right? Those are the situations where, the system is truly in one of those Schrodinger's cat state, completely fuzzy. You cannot say whatever it is. So you're looking at signals, in this case, we put a mannequin behind an occlusion, right? And traditional system will show you almost nothing, or maybe the occlusion itself, right? We can actually recover all this, and you can see that the mannequin full details behind. I'll show you the difference when you actually look at this with or without, this type of enhancements, right? And how you keep, as you keep learning on this, how this becomes better and better. You see, as you keep learning from the before and after, it gets better and better. You see that the mannequin is a little bit animated in full details. You can pick up contours. Again, you can classify geometrical in this. There's so much. These are like some of the applications we built. Just the beginning, we just started scratching the surface of this, what we did in a few weeks. And the idea is like everyone can build this kind of application, can really take it to the next level. How powerful it is, you can actually win over abstractions. It's a big pain in the industry. Everyone knows pages, water, mud, bugs, all the stuff that ends up on our windows. And people are just trying to solve it with brute force. Oh, windshield wipers, more power, right? No, better, different sensors, right? You can be smart about that, and win at that. So this is like our tower provided by the city of New City to us. They built it for us 400 meters away from our lab. We don't pay for it, but it's a beautiful test. So this is one of our actual probes, the optical probes. Next week you see there's also camera probes looking at that. And so we'll show you some comparison when you actually put stuff on it, what it's now. So on the left, there is actually the picture, the point cloud shown when there's no objection. The window is clean, there's no dirt, no water on it, right? On the middle one, you actually see after you put a lot of dirt. And there's still no spatial algorithm. This is sort of like a classic canonical conventional approach, like things are done today. And by the way, we're still at 400 meters. People don't see at 400 meters, but let's suppose the industry will see at 400 meters, right? And that's how we see. And then we actually kick on our perceptive sensing approach, right? And that's how you can actually see that the resulting image is actually even better than image without abstraction. So this is like with abstraction, and it's better than actually when we didn't even have water and dirt on the window. This is another example of how, when you actually, we talked about insights, we talked about picking up clues and talking about context and cross-modality kind of relationships between the different signals, the different physics. Millimeter waves look at the world in different ways, optics and lasers tell you different things. So when you actually put them together, well, 1 + 1 is greater than 2. So in this case, you can actually see a typical, very simple example. One of our first radar. I really love this demo. It's all, we've done so much more today. We have higher resolution and so forth. But I love this because it's so fun. We built this thing with a few $100 off the shelf to demonstrate the power of the algorithm. But we had the raw data, right, already at the time. And so you see on the left side, there's a camera. Then there's like a point cloud view from the laser probes. And then you can actually see the radar view. You see the radar view in the middle is like all this purple cone. It's noise. That's what you get from a cheapo. Like we build it off the shelf with TI components, right? And what we have now, I'll play in a second, you have two vehicles. One is moving away from us. One is coming towards us. And the visualization you see on the right is actually the concurrent sensing view of the world, when these modalities are all coming together. Again, look at the contrast that you actually see. There's a vehicle coming towards us, colored by actually Doppler velocity, and a vehicle is going away from us. So you have enhanced the kind of, let's call it SNR here, by a factor of 100, in software, without spending a penny more on the hardware, right? So we could have done this two ways. We could have picked up a military-grade radar, spent millions of dollars, hired a team, spent a few years. Or how about you pick up the raw data? You look at that in light of what actually the other modalities are telling you. Game changer. Again, look at the power of actually when you apply this even to our cross-modality view of the world. This is the ability to actually extend your typical range of your modality, to see much more in the higher details, in higher context, but again, by bringing together all these pieces. This is a point cloud, which is actually obtained through our algorithms. Looking at extremely far range, we follow in a vehicle in this case, we track exactly the velocity of every single piece to the millimeter per second, right? And you can see this going on hundreds of meters, 450 and beyond, right? In extreme high details. This is actually how a live object looks like at 400 meters. The picture is static. It's taken at 400, by the way. We're shooting at 400. And what you see there is actually frame per second in a thousandth of a degree. You can see facial contours. You can see the car in extremely high details. You can see the dynamics. See an object colored actually by the different velocities of the body posture. It's actually getting around. This is actually Reza at midnight at the Levi Stadium down in San Jose. It's the only place we could find where it's 400 meters clear without the cops. Yeah, that's a big problem. So yeah, look at the details that you have there. You can see the rack, and like, again, there is so much. We're showing intensity actually and some velocity, but we have all this additional 20 dimension and more that you actually, in the signals carry there. And this, I mean, it's all these, some of you may have seen it. We're at Stanford, I work here, so we have to, like, it's our favorite, it's beautiful, it's our oval. It looks like an aerial picture, but we actually took it from one of the corners of the oval. You can see the Hoover Tower, which is at more than 400 meters, incredibly high details. We measured it was actually a little bit more than 60 meters tall. This is actually another powerful application. We talked about all the things you could do now. You have this ability not only to get the data that goes up from the hardware to the software, but you can go from the software down to the hardware in real time, close the loops, right? And actually encode attention and adaptive algorithms, right? So this is one case. Driving on El Camino, I see vehicles colored based on velocity. Effectively, we have a just very sharp kind of coloring now, but basically red means it's actually going away from us, or green means it's coming towards us. And driving on El Camino, and the system is really smart. It's actually allocating attention based on what's in the scene. It knows what it's looking at. So there's horizon, there's the road. It's actually shaping attention based on the shape of the road. It segments, understands where the sky is, where the trees are. So it's actually doing that all the time. At some point, we drive by a construction site, and we pick it up. And then we decide to actually kick in the algorithms that emphasize the road structure. You can see cones, construction cones. You can see the cranes, construction workers in details up to hundreds of meters, right? So that's something you could have totally missed if we just kept looking at the world like naively, like not making any assumptions. So it's really powerful. And you can implement a ton of these things because you can determine at will what your priority is. You can encode your prioritization in these approaches, right? The API allows you to do all these things. Any user might have different applications. These are some actually other examples of our powerful approach. In downtown Redwood City, you can even pick up road markings. There is no saturation, extremely high resolutions, built with little, right? This and extremely high details. Or again, these things. There's a lot that we do to actually understand the gaps, right? Because if you have an object, it looks like a truck, and there's points that you miss in the system, is really smart. And so you end up with these incredibly high resolution representations. You have 6 million points per second in this representation. So all this is happening in real time. Some people cannot even digest them. And this is just the no-raw data. Like, the raw data is huge, right? But the power of actually being smart and attentive, look at it on pedestrians. Left side, you're now being attentive. Right side, you're being attentive. There are people at 150 meters there, you would have totally missed them if you just look at the world like a dumb fish. Not making any assumptions about how the world looks like. I look at it differently. You can see the velocity. You can actually expect the project where they're going to be going. You can see their vectors. And this is one of the favorite ones. And this is like, we show you some of the things studied, but this is actually driving. Driving on our roads, and you can see how we can actually, we're driving and following the vehicle, and we can track it and follow it increasingly high details. So it's not a trade-off between long range and mid-range and short range anymore. You can get it all. So this is actually a pickup truck or vehicle following. You can see different representation of the intensity on one end, and then two different representation in 3D played around on the bottom, right? So look at the details of the vehicle. It's crossing 300 now. Full details. You can see a pickup truck. 350. Keeps going. 400. Right? We still have the scene. Look at the close scene that you see in the front. Top left, you have incredibly high details. Keep going. 400. And it keeps going. 450. Keeps going. So, we show you the system today. We show it says complete rethinking, reimaging everything from scratch. It took us a while to do it, but we really wanted to take a very different direction, right? Really excited about autonomy. We wanted to enable it. So it's really integrated. It's multiplex, which is a point exactly. It saves you a lot of components, a lot of hardware. So because the hardware is centralized, you don't have to buy 20 of one thing. You have it there, right? It's digital, so finally it changes completely the game. This becomes a software business, right? It's concurrent, it's perceptive, really understands what it's seeing, right? It uses all the intelligence that we couldn't even do before because the compute was not even available at this stage. It's attentive, it can adapt in real time, and it's software defined. It's a platform for everyone to develop on. So that's super exciting. It's a ton of things. We flew over a lot of details. We're going to be here around. We actually have to be here. We have a vehicle outside with a system, fully integrated, 360, multiple of these probes going around. You can see some of the photonics components we've actually realized. There's so much in this. Again, I haven't got through the detail. Ask me more questions. I'll be around here. If you have to run away, reach out at info@perceptivesensing.ai or to our website. Please reach out. Happy to answer your questions. But there's more. There's more. We talked about, we've done an amazing job here, right? But anyone claiming that they have the final, best, perfect solution to sensing and perception is lying or is a fool. There's no such a thing. There's no limit to how good a sensing system can be. The sky is the limit. Ingenuity is the limit, right? This is an ongoing process. So as opposed to hard code, just a solution in a system, we wanted to actually create a platform that really create a new open-sided possibility for a class of iteration for the industry to develop upon. That's when we actually opened up to all the intelligence, all the smart folks in the companies represented here today, then you really change completely things. So this has to be an open platform for everyone to develop on. And so we're really, really excited today to actually, we've been partnering with several companies, but we're excited to actually call on the stage one of the best radar companies that we know about. We've been absolutely astonished what they've done. We love their architecture, we love their approach. They're changing the game on radar. They really understand there needs to be a change. This is a new take on radar. It's a 4D imaging radar with complete access to raw data, a lot of intelligence, and a completely novel architecture. And it couldn't be a better fit than actually a developer for applications on top of the Perceptive platform. And so I'm excited to invite on the stage today the founder and CEO of Zader Labs, Mahmoud.
Thank you, Alberto. Thank you for your kind words. Great to be here. A lot of exciting stuff. So I'm Mahmoud, the co-founder and CEO of Zader Labs. I'm here with Mo, my CTO and co-founder. We're actually about the same age as Perceptive, and it's funny, Alberto, Reza, and I share a lot of milestones in our career. We all went to Stanford, all went to Apple Car Project at some point, and the startup journey kind of overlapped completely. Let me take 1 minute and tell you about Zader and why we started this company. So Mo and I were working on autonomous vehicle program, and we realized that radar technology is usually the third modality in the perception stack. Most of the AV programs are utilizing camera and LiDAR for the perception needs. And radar, it's a very mature technology. It's commonly used today for ADAS functions like emergency braking. The problem is it doesn't have the imaging capability or the resolution that LiDAR and camera have today. So because of that, it's underutilized today. But the opportunity here that's missed in radar is that radar has two unique properties that's very powerful for mobility applications. One is the Doppler. So in each scan of radar, you get the motion, and that's very important for moving application, as you can imagine. And the second is the all-weather robustness of all-weather operation, robustness of radar. It doesn't depend on lighting condition or rain, fog, dust. Radar sees the world the same way under all operating conditions. So we looked at a lot of radars on the market from tier 1 companies, some startups, and realized that, oh, there's a big gap between what's available today, actually 2 years ago, on that time, and what the AV and full autonomy needs. And we looked at all the existing technology, the latest silicon technology, processing technology, and we decided to work on this problem, focus on this problem. And fast forward today, after more than 2 years, we built 3 radar sensors. These are all 4D imaging radar sensors with different form factors for different end applications. We're not looking at only autonomy, we're looking at industrial automation, security surveillance, smart infrastructure, robotics. There's a lot of applications for radar. And these are, the nice thing about radar is it's very manufacturing friendly and it's very low cost. So our Z-Prox sensor, for example, is a 4D imaging radar, it's only $10 bill of material cost. So then, during these past 2 years, we exchanged ideas with Alberto, and we definitely share the same vision that Right now, these are standalone imaging radar products, but if we have the context, if we have the information from the other sensors, for example, LiDAR, camera, or INS, IMU sensors, we can do much better detection on our radar sensors. Today, actually, we use, for example, INS, IMU data that's fed back to radar, and that actually helps us a lot in our detection. So it's very obvious to us that what Alberto and his team is building, it unlocks a lot of value from the perception system. So that's why we decided to team up and bring our radar front-end technology to Perceptive platform, and now we basically compile our detection algorithm and signal processing engine and AI with the help from the other basically probes that Alberto has available on Perceptive platform. And with that, we're developing different applications that now do the AI of different use cases with the help from other probes that's available on Perceptive platform. So, so just a quick overview of the 3 sensors we've built so far, and there's more products coming out. Z-Clocks is the smallest sensor we've built. It's good for automotive application for surround view with radar as a replacement for traditional ultrasonic sensors that are pretty basic. This is a 4D imaging radar. Can see up to 50 meters around the vehicle. Z-Signal is our mid-tier product. Can see up to 250 meters with this form factor. And the Z-Front is the highest performance sensor we're building. This can see targets up to 800 meters with a 0.4 degree resolution, approaching LiDAR-like point cloud, and specifically targeting high-end applications like level 5 autonomy, autonomous vehicles, and trucks. In terms of our approach to building the radar, so we're taking a basically a ground-up approach. We don't do any custom silicon. We're using the existing silicon devices that's proven from global semiconductor suppliers and processors. We build our radar system, an antenna design, and array design around it, and the main innovation here is the radar signal processing engine that runs on all of these sensors, embedded software that runs and basically creates the point cloud. So now we're bringing these platforms to Perceptive. Instead of running the radar signal processing engine, we're bringing our raw detection to the Perceptive engine, and now we can do these applications with more capabilities based on our radar signature or radar echoes from the environment, and also the other multimodal probes. So we define some of the apps that we can, right now we've developed them standalone with our radar technology, but we can now improve their performance, precision and recall, which is ultimately the perception metric when we have the data from other probes. To give an idea about how 4D imaging radar sees the environment, you've seen probably camera and LiDAR data. So this is a Siemens Mobile near our office in San Jose. We're driving. On our vehicle, test vehicle, we have 4 Z-Signal sensors. This is collected with 4 Z-Signal sensors to cover 360 view around the vehicle. And this is a point cloud of all static objects and moving objects. Maybe I should say it one more time. It's the 3D point cloud. Each point has also velocity information or Doppler information, so you can see static targets on both sides of the road. The vehicle is at the origin, at the coordinate, and you see the vehicles following us or going away from our test vehicle. So thank you. Very excited about this partnership, and we believe that a lot of good outcome for the autonomy community will come out of our radar technology with Perceptive platform. Thank you.
So that's exciting. I mean, really, I've seen radar companies claim they're innovating, but not many, but this is a really different game. So again, wrapping up, we talked about a high level, we gave you some data, there's so much, it's a lot of details we didn't talk about, how we reduce the number of components by 90%. Power consumption is going down almost 90%. The APIs we actually build for people to interface, all the different channels and dimensionality of the signals that we get, the silicon photonics approach, the CMOS approach. There's so much into this. Really, it's novel. It's really a lot, but I'm really looking forward to tell you all about this. So the system is available now. Production is available this fall. It's available for pre-order today. We are looking forward to partner, engage with more people. So please let me know if you have interest. And I want to sort of basically realize that I think we have an opportunity today. Really, this is one of the moments to really make one of those tectonic shifts in technology. You've seen a few of these. They really happen over 5-10 years. No one controls them. It just happens. And the trend has been, since the 80s, basically bringing technology closer to us, making it more and more personal. And ideas like technology is finally coming from our desks to our pockets, and then finally really talking to us, becoming one of us, right? That's the idea. So until we just have tools, really our life only changes so much. When actually technology becomes truly integrated with our intelligence, that really changes the world. So we had a lot of progress in digital world AI in the past 10 years. It's been almost 10 years since ImageNet also that kicked off here, right? Now it's time to bring AI to the real world, and that's where robotics is, that's autonomy is, and it's happening today. So thank you very much for coming. I'm super excited to show you this. We're around. We have a vehicle parked outside. If you want to take a peek, some of us will be outside to answer your question. We're around. We have the venue until people want to stay. There's food, drinks, music, so enjoy yourself. Thanks for coming.